Hello and welcome to a video where we're going to be starting off a new topic all about waves. Now this isn't the waves as in like a Mexican wave or wave at a friend. This is waves as in physics waves, waves of sound and light. So the first video that I'm going to be doing is about sound. So can you put your title as what is a sound wave? And we're going to go into a bit more detail about that. We're going to describe how sound is produced, and we're going to look a little bit about the speed of sound. So, first of all, let's move on. Still got the title there, medium. If I ever use this word, it is the state of matter of the substance the sound travels through. So, air is a gas, walls is a solid, water is a liquid, vacuum, that is empty space, that's up in space. There's a vacuum. Okay, no particles in there, that's important, we're going to talk about that. The speed of sound. The speed of sound is 340 meters per second, whereas the speed of light is 300 million meters per second. A lot of difference there. Okay, so we're going to talk a bit about how we generate sound. So I would like you to put your hand on your throat and just talk, hum, speak, and you will feel vibrations in your throat. And that is what sound is. Sound is just vibrations. It is particles vibrating, hitting into another one and transferring the sound. And you can see it. Put your hand gently on your throat and hum. Can you feel your larynx vibrating? So that's in your throat, that's for your voice box, which allows us to speak. Now, I haven't got a tuning fork, I would love to do it, but when you hit them, they slightly vibrate. So, sound, if we look at this, sound waves are caused by vibrations. You create sounds by vibrating your vocal cords, that's part of your voice box. Sound needs particles to travel through, okay? And if we go back to here, vacuum is empty space, it has no particles in. So sound cannot travel through a vacuum. And this is why they say nobody can hear you scream in space, because you're not able to send sound across a vacuum. You need particles, whether that's air particles around us or a particle in some solid or liquid, but you do need particles. Sound waves are longitudinal. We'll touch upon this at another point, so don't worry about this one too much. Sound waves travel quickest through solids. Now let's have a think about why sound waves might travel quickest through a solid. So in a solid, the particles are all really close together. In a liquid, they're close, but they're a bit more spread out. And in a gas, they're all over the place. Now, why might sound travel through here quickest? That is because the particles are touching one another. So when this one vibrates, this next one vibrates straight away. And the next one vibrates straight away. And the next one vibrates straight away. And the next one vibrates straight away. In liquid, they're not as close. It takes a little bit of time for them to transfer the vibrations across, whereas in a gas, it takes a lot longer. However, you might think that talking through a solid would be the best way to talk. Because it travels so fast, it doesn't travel as far, whereas in gases, it travels a lot further. So, to revisit, it travels fastest for a solid, so fastest through solid. So fastest through solid, whereas it's slowest through a gas. So vibrations are the cause of sound. So anything vibrating will create a sound. That's like your phone. Your phone will vibrate when a message comes through, and that creates a little bit of sound. Another thing you can do is if you've got little speakers or something, or speakers on a TV, or speakers on a laptop, speakers on your phone, if you turn the music up full and you put your thumb or finger on the speakers, you will feel the vibrations. Right, next, don't worry about that. So, speed of sound, we said, was 340 meters per second. Sound travels via vibrations from one particle to another. Sound waves travel fastest in solids and slowest in gases, and that's what we just talked about here. Okay, so that's the first bit done. Let's move on to the next one. So now we're going to talk a bit about the loudness, the volume, how loud sound can be, and the pitch. So, loudness and amplitude are linked together. Frequency and pitch are linked together. Please make a note of that these two are linked and these two are linked. You will need to know that. So, pitch is how high or low a sound is. So when you go really high, you're shocked about something and your voice goes really high, that's a high frequency. When you're really low, that's a low frequency. And we're going to talk a little bit about that in a moment. Amplitude is what we call the height of the wave, or how loud it is. The greater the amplitude, the louder the sound is. So when I was in the classroom and I would get your attention and I'd be the loudest person and cause you all to listen to me, I had a very great amplitude. Whereas when I was being quiet and I was just talking normally, I had a lower amplitude. So we're going to talk a little bit about different waves. Do not worry about infrasound and ultrasound. You might have come across these before, but don't worry about knowing these off by heart. But this bit up here, the pitch, amplitude, and their definitions are very important. So if you've got a ruler, you can do this little activity where you twang at the free end and produce a sound. This is just looking at ways you can make it vibrate faster or slower, and that links to pitch. So I'll do that in a moment. Right, let's have a look at different diagrams here. So we have got low amplitude, low frequency. So low amplitude, low frequency. So this would be quiet. Quiet plus low sounding. So it'll be very bassy, is what we'll call it. This one, low amplitude, so it'll be quiet. But it'll be very high pitched and squeaky, so it'll be high sounding. I'm going to put squeaky in brackets just so you can get an idea of what it should sound like. This one is high amplitude, so it's going to be loud, but low sounding. Again, bassy. And this is high amplitude, so it is loud, and high frequency, so it is squeaky, just like the one above. Now this is where we get to draw waves, and our waves look a bit like this. Going up and down across a middle point. I know this is a terrible drawing and you can probably draw better, and I will get you some diagrams of this onto Google Classroom and you'll see some better pictures. But the amplitude is how high the wave goes. So this to the top there, to the bottom, is our amplitude. And our frequency is how many times we go through one wave. So the wave starts here and ends here, and then restarts and here. So the frequency is how many times through we go. So a higher frequency will squish them together. So we'll go in that sort of direction, we'll squish them into each other, and a low frequency will spread out. So let's draw these. So low amplitude means we're going to have a small crest. It's not going to be very tall. It's going to be small, and it's a low frequency, so we're not going to repeat ourselves that much. Again, you'll probably draw better than I will, but you can see it's spread out and it's quite small. Now this one's low amplitude, so it's small, but it's a high frequency. So it will only go up to this one, but it will happen often. Can you see that this one has more peaks at the top? It's a lot more squished, so it's a higher frequency than this one. So that's what will make it a squeakier sound. Now this one is a high amplitude, low frequency, so it's going to be spread out because it's not very frequent, but the high amplitude means it's going to be very tall. So we'll go up to the top, and we'll go back down, okay? Actually, let me draw that one a bit better. So as I said, high amplitude will go to the top, but low frequency, it won't happen too often. Okay. Same with this one, it's about a similar frequency to this one, where we've only got one peak and one bit at the bottom, but it's a lot taller this time. So therefore, it is very loud. This one is high amplitude, high frequency, which is a very loud, squeaky noise. So we'll go up, and back down, and up, and it will continue like this. And as you can see, if we compare these two here, it's the same height, so it's the same amplitude, it's as loud, but this one is a lot more peaks and troughs going on, and therefore it's a lot squeakier, it's a lot higher pitched. So we've got low amplitude, low frequency, through to high amplitude and high frequency. If you have a high frequency, you get a squeaky sound, you get a high pitched sound, it's very high. And if you have a low frequency, okay, it's a low, deep sound. The bassy sound, I was saying. And then with amplitude, a low amplitude is quiet, and a high amplitude is loud. So you need to make sure you can understand the differences between those. So I would heavily recommend copying these diagrams and putting the notes around it. So, as we have just had a look at, this is another example of the wave. This is a lot better than my drawing. You can see we've got the amplitude being A, that's from, it can be from the top to the bottom or the bottom to the line, as long as it's from the line to the top. Then you've got the trough, that's these bits at the bottom, the peaks at the top. It's just ways that we name them as being peaks at the top, troughs at the bottom, and then C being the peak, yeah. Now, there's something called wavelength, but don't worry about that, we'll go into that one a bit more detail when we do light. Right. So, a loud sound has a bigger amplitude, or bigger amplitude as it says here. So as I was just talking about, the high amplitude equals a loud sound. High pitch is a high frequency. Now, it says here about different animals having different ranges. That's true. Dogs will have a lot more sensitive ranges, so they are able to hear things at a higher frequency. That's why if you've ever had something called a dog whistle, we can't hear the dog whistle, but dogs go crazy and they start to hear it and they don't like it. And that's because their ears are a lot more sensitive than ours. And I'll link a website that you can listen to, and you can understand different frequencies and you can play them out loud. Please don't play them out too loud. People have different hearing senses. I don't want you to annoy your family, but it's just a good idea to listen to. Right, now we move on to the next bit and the final bit of this video, all about ears. So we're going to talk about how ears work. So we have got our ear here, and we've got our labels. So we've got our pinna, we've got our eardrum in the middle, we've got our ossicles, we've got our cochlea, and we've got our auditory nerve. Now the auditory nerve links to the brain. Okay, the cochlea is filled with fluid. This helps with our balance as well as other parts. This bit in here is our 3 little bones that help produce sound, and the eardrum is what vibrates. Now we're just going to quickly go through what happens when you hear something. So let's get the pen up. Sound is caught by your pinna. Sound is not as good as my other. Sound is caught by pinna. Sound is caught by the pinna, and then it is is kind of guided down into your ear canal. So your ear canal then collects it, it vibrates through your ear canal, and then it starts to vibrate to the eardrum. So it vibrates. I'm just going to put B because you can see it there, vibrates B, and we know that's the eardrum because it says B here, eardrum. So it vibrates B. Once the eardrum has started to vibrate, then these parts then vibrate, and it starts to create an electrical signal, and the electrical signal is then sent to the brain, and the brain translates it into what we hear. So when you hear things, what's going on, as I said, is the sound is caught by the pinna, guided down your ear canal, and it vibrates the eardrum. Once the eardrum starts vibrating, these parts then start vibrating and generating an electrical signal, which is sent by your auditory nerve to the brain. And that is how your ears work. So, put these into the right order. Sound waves are collected by the pinna. Sound waves travel through the ear canal. Sound waves make the eardrum vibrate. Vibrations travel through small bones called ossicles. Vibrations pass through the cochlea. Vibrations change to electrical signals, and the electrical signals are transmitted through the auditory nerve to the brain. So I'd like you to make sure you've copied down the diagram. Especially, I'm not expecting you to draw this, or if you want to find one online, you can Google it and find it. But if you can just gently draw this out a little bit. Actually, what I'll do is I'll link you a file so you can see what the ear looks like, and just make sure you've got the order of what happens. So that is a quick video on sound, what generates sound, and how we hear. Thank you for watching.